Good morning, everybody. So today we shall start our discussion on fiber optic gyroscope. An inertial gyroscope, of course, require very high sensitivity, and because that finally the whatever be the angle measurement is integrated over a long time and to give an accurate result. Unless the sensitivity and offset error is low, so there will be large error when it is integrated over a long travel time. So here mechanical rotation of a fiber optic coil produces a phase shift in a Sagnac interferometer. Of a fiber optic coil produces a phase shift between two counter propagating waves. Two counter-propagating light waves in a Sagnac interferometer. Now, Sagnac interferometer is a closed loop configuration. So here we have a laser diode. This is the lead fiber. This is a beam splitting prism. So which split the light from the laser diode into two components. So one component which is directly coming from here just after the source. So I think photodetector can be put here. Then this is the electrical feedback to stabilize the output of the laser diode. So from the lead fiber, unlike in the previous case where we have directly fiber coupled, in this case This is again coupled by another beam splitter here. So this beam splitter, because the fiber coil which is placed on a rotating inertial platform should be free to rotate. So therefore the coupling is in free space. So this is the sensing coil. Has to be aligned with this point where the outgoing beam is interacting with the return beam. There is a piezoelectric driver which is basically giving some strain to this second coil, producing a phase shift, a DC phase shift at a frequency omega m. Because the shifted frequency, we have to give a DC frequency in the frequency shift to know the direction of the rotation of this sensing coil. This sensing coil is mounted on a platform. So usually the rotation of this coil perpendicular to the plane of the coil. So that is the requirement. This PJT driver is here for the phase modulation. Then we have this is driven at a frequency of omega m. Now this return light goes back through the lead fiber, which is already interfere at this point. So the intensity modulated light is going back, and this light is reflected this way because of this prism, and we have a photo detector here. This could be PD1, this is PD2. And then this is fed to a lock-in amplifier whose reference frequency is this omega m. So the PJT basically serves two purposes. One is that it gives a shift in frequency, constant shift to decipher the direction of the rotation. So this one rotating at capital omega. So if we assume a single turn coil, usually there are n number of turns are there, or maybe let us assume n turn coil. That we can do later. Single turn coil, the two counter propagating beams. Two counter propagating beams will return without any phase shift. Will return maybe in this case with a constant phase shift. With a constant phase shift. Corresponding to the phase modulator. With the rotation of omega, with the rotation of capital omega, one wave will be propagating in the rotation and another will be propagating opposing to the rotation. One beam so basically here also we have a counter propagating waves are there because this is a beam splitter. So this one is coming in, so one component is going in this one and another component is coming in this direction. So this one is going back this side and this one is going back from this side and two will interact in the return path. One beam will propagate with velocity c plus r into omega. Capital R is the radius of the coil. And another with the velocity c minus r into omega. R is the radius of the coil. So therefore, the time taken by the two coils, two beams will be twice by r, that is the length of the fiber in a coil, divided by c plus r capital omega, and twice by r divided by c minus r capital omega. Therefore, giving a differential time, therefore the delay relative delay delta t would be twice by r into 1 by c minus r omega minus 1 by c plus r capital omega. So which is equal to 4 pi capital omega r square divided by c square minus r square omega square. C is the velocity of the light in the coil, which is much larger than r omega, which is the linear velocity of the coil. Since velocity, light velocity c much greater than r square omega c square, much greater than r square omega square, delta t can be approximated as 4 omega pi r square can be pi r square by c square. So this can be also written as 4 capital omega. A is the area of the coil by c square. So now in terms of phase shift, phi would be equal to twice pi into delta t into f. This f is the frequency of light. Now this F also can be expressed in terms of lambda. So that is the wavelength that would be given by 8 pi. If I put the delta values here, so finally we will have 8 pi omega into A. C is the velocity, so one C will go for this lambda, another will be here, lambda 0 into C. So for n number of turns, of course, capital N number of turns, this will be equal to 8 pi capital omega A into N by lambda 0 into C. So because this coil has to be free from any other kind of perturbation, so therefore usually the area or the radius R of this coil made very large. The most important perturbation is that when we bend the coil, there will be some amount of stress generated in the fiber, and with temperature variation that usually changes, and that gives rise to a drifting effect. So therefore, generally for the sensing coil, special fibers are used. For example, circularly spun fiber. These are kind of optical fiber. Optical fiber are generally a silica rod is fused with differential index profile, and then wire is drawn similar to that copper wire or other kind of. So that wire is drawn and put on a drum. So depending on the tension, the radius of the wire will change. So now, in case of circularly spun fiber, while the fiber is drawn, that is also rotated. So that is to fuse some kind of rotating stress in the fiber to reduce the effect of this bend induced stress. That rotating stress usually will be the dominant factor, and this bend induced one, which is towards the outer towards the uh, radial directions of the fiber, is linear change, so that effect will be reduced. So and also To reduce that bend effect, the radius of the coil is made large. To reduce the bending stress, which is temperature dependent. The other way is that to maintain the temperature of the fiber optic sensing coil. Because typical demand for resolution of rotation, that is this capital omega, is in 10 to the power minus 6 or 10 to the power minus 7 degree. So such high resolution can be done without much noise floor. We need to control the temperature. So we can take one example. Suppose N is equal to 1000 tons. R equal to 0.1 meter. Say capital omega equal to 15 degree per hour. That is the earth rotation. And so this 15 degree per hour, we can convert 15 by divided by 180. (3600 radian). And for simplicity, let's lambda equal to 1 micrometer. Usually it could be 830 micrometer or so, based on the availability of the fiber characteristics and the laser diode, but we can take 1 micrometer. So with this say delta, this phi will be 8 pi into 15 pi thousand turns, then another pi 0.1 square divided by this one 180 3600. Lambda in micrometer, so 10 to the power minus 6 we have to put in meter, then C. Roughly assuming the velocity at vacuum, though it won't be like that. Actually, it will be reduced due to the refractive index of the optical fiber. So that it will be 1.5 also, but let me assume like 3. So that approximately 1.9 into 10 to the power minus 4 radian. So that will be the phase shift. So therefore, because this phase shift is very small, so we need to measure it very accurately. And this lock-in amplifier enhances this measurement because it filters out the background noise, and it only picks up the modulated one, which is at omega m, and fed as the reference frequency to the lock-in amplifier. This is the principle of gyroscope. Next, we will discuss about another application of Sagnac interferometer. So the principle is very similar, so that I can discuss it today itself. That is fiber optic current sensor. We have seen the fiber optic magnetic field sensor. So that has been implemented with Mach Zehnder configuration, but typical fiber optic current sensor for large current fiber optic current sensor for large current usually done using Sagnac interferometer. So here again it is very similar. We have a fiber optic coil which is wrapped around a current carrying conductor. I mean, a current carrying conductor is not wrapped around, passing through the between the coil. So it need not be wrapped around. If we wrap around, then the temperature effect will be quite high. These are usually used for sensing large current in kiloamperes or megaampere. This is the sensing coil. So basically, if we put a coil around a current carrying conductor, which is a straight conductor, the magnetic field will be parallel to the light wave propagation. Now, just like before, we have a PZT modulator here. Phase modulator. The driver of the phase modulator. Lock-in amplifier. Photo detector. Then is the reference. And we can have the output. So this is a fiber optic directional coupler. Which basically couples the light when it is coming from this direction. It does not couples the light when it is coming from this other direction. Now this one is a fiber optic polarizer. This is called lambda by 4 plate, which give a 45-degree shift to the light polarization. This is another lambda by 4 plate. That is known as quarter wave plate. So light goes in this direction and also comes back. So this 50:50 splitter, two component pass through this same configuration through the coil, and then we have a relative phase shift. This is done by measuring polarization rotation. Phi of a linearly polarized light. So this phi, you know that light, there is something called polarization. That is nothing but the direction of the electric field vector. And a polarizer is a device which basically aligns the electric field vector along a particular directions. Now, a fiber optic polarizer is such a device that it attenuates light's electric field vectors which are in some other direction and preferential to a particular direction. Okay. So then the light becomes linearly polarized. You might have seen, some of you, that those polarizers used in camera to reduce the reflection, effect of reflection. Because when light is reflected, light gets partially polarized. And to reduce that effect of reflections, we can put a polarizer. And if we rotate the polarizer appropriately, the effect of reflection will be reduced. So this polarizer basically makes the light linearly polarized. And this phase modulator, of course, just drives at a particular frequency omega m, and that omega m goes to the lock-in amplifier at the reference frequency. However, that does not change the rotation angle. The rotation angle is changed by this quarter wave plate. So that gives a bias, and there are two quarter wave plate, 45 degree, 45 degree. So that splits that linearly polarized component into two equal orthogonal polarized component, and such kind of light is known as circularly polarized light. So then the rotation phi induced by the magnetic field is related by mu p line integration of h dot di. V is a Vedet constant, named after the scientist. So which relates the polarization angle rotation to the magnetic field. So because this is a line integration and a dot product, so basically this takes only the in plane components. So therefore the light is made to propagate along the magnetic field, and that's why the current carrying conductor is here, and the magnetic field will be circulating around that, and the coil is also in the same plane. Okay, so thereby the direction is same. Now, for a closed loop configuration of n number of turns, if we integrate this magnetic field, that becomes simply Ni. I is this current. So this is the basic of this current sensing. This is again the configuration is Sagnath interferometer. Now, just like the previous fiber optic gyro, there will be +5 phase shift for one direction propagating wave and minus 5 phase shift for the another uh, propagating wave. So together they will have a differential phase shift of twice 5. Okay, so that will be interfere here, and then that has been passed through this polarizer again, because that interference will affect to other stray light components or other component which is not modulated. So all those are filtered out again by this polarizer, and finally through this directional coupler it is guided to this fiber and to the photodetector, detects the modulated light and shift intensity modulated light at omega m, and which is fed to the lock-in amplifier. So lock-in amplifier, because of the reference frequency omega m, measured the amplitude of that modulated component only. So we will discuss little bit maybe next day. Today time is